Have you ever wondered what it really means when scientists say something travels at the speed of light? We've all heard the term thrown around, light speed, 299,792,458 meters per second. But what does that actually mean for our universe, for space travel, and for the very fabric of reality itself? Today, I'm going to break down one of physics' most fundamental concepts in a way that finally makes sense. By the end of this video, you won't just know what light speed is, you'll understand why nothing can move faster, why it matters for everything from GPS satellites to time travel theories, and how this cosmic speed limit shapes the universe we live in. So, if you're ready to wrap your head around one of science's most mind-bending ideas, stick around. And if you find this helpful or interesting, hit that like button. It really helps the video reach more curious minds like yours. And if you want more content breaking down complex science into clear explanations, go ahead and follow so you don't miss out. Let's dive in.
Imagine you're standing in a field on a dark night, looking up at the stars. What you're seeing isn't actually happening right now. You're looking into the past. The light from those stars has been traveling through space for years, decades, centuries, or even millennia before reaching your eyes. This is because light, despite being the fastest thing in the universe, still takes time to travel. Welcome to the fascinating world of light speed, where physics becomes poetry and our understanding of reality transforms completely. What is light speed? Light travels at approximately 299,792,458 meters per second, or about 186,282,000 miles per second. For simplicity, scientists round this to 300,000 kilometers per second, or 300 million meters per second. Let's call this cosmic speed limit c, as physicists do. But what does this number actually mean? To put it in perspective, light could circle the entire Earth about 7.5 times in just 1 second. If you could snap your fingers and send a light beam racing around the equator, it would complete those 7.5 laps before you finished snapping. That's incomprehensibly fast by human standards, yet in the vast expanse of space, even this incredible speed seems almost leisurely. When you flip a light switch, the room illuminates almost instantaneously because light reaches your eyes in just billionths of a second after leaving the bulb. The distance is so small that your brain can't perceive any delay. But stretch that distance across space, and suddenly the speed of light becomes our window into cosmic history. Light speed in everyday terms. To truly grasp how fast light travels, let's break it down with some relatable comparisons. If you were to travel at the speed of light, you could go from New York to London in about 0.02 seconds, or roughly 1/50th a second. You could reach the moon in about 1.3 seconds. That journey takes astronauts 3 days using conventional rockets, but at light speed, you'd be there faster than you could say, "Houston, we have no problem." Let's think about something closer to home. When you're having a video call with someone on the other side of the world, you might notice a slight delay in the conversation. This isn't just because of internet lag. There's actually a fundamental physical limit at play. The signal has to travel through fiber optic cables, bouncing as light through glass, and even at light speed, crossing half the planet takes a measurable fraction of a second, usually about 0.05 to 0.1 seconds for the signal to make the journey, plus processing time. Here's another mind-bending fact. When you look at yourself in a mirror, you're seeing yourself as you were a few nanoseconds ago. The light has to travel from you to the mirror and back to your eyes. If the mirror is 1 meter away, the light takes about 6.7 nanoseconds for the round trip. It's imperceptible to us, but it's real. You never see the present moment, you always see the past, even if it's the tiniest fraction of a second ago. Why can't we go faster? Here's where things get truly interesting. Light speed isn't just fast, it's the ultimate speed limit of the universe. Nothing can travel faster than light. Not spaceships, not particles, not information, nothing. But why? The answer lies in Einstein's theory of special relativity, published in 1905. Einstein discovered that space and time are not separate things, but are woven together into a four-dimensional fabric called space-time. As you move faster through space, something bizarre happens. Time slows down for you relative to someone who's standing still. This isn't science fiction. It's been proven countless times with precise atomic clocks on airplanes and satellites. As an object accelerates closer and closer to the speed of light, several strange things happen. First, time dilation becomes extreme. Time slows down dramatically for the moving object compared to a stationary observer. Second, the object's mass effectively increases. The faster you go, the more massive you become, and the more energy you need to accelerate further. Third, lengths contract in the direction of motion. A spaceship traveling at near light speed would appear squashed to an outside observer. Here's the catch. As you approach the speed of light, your mass approaches infinity. This means you would need infinity energy to actually reach light speed. It's like running on a treadmill that keeps getting steeper the faster you run. Eventually, you reach a slope so vertical that no amount of effort can push you forward another inch. Light itself can travel at light speed because photons, the particles of light, have zero rest mass. They're born moving at sea and can never slow down or speed up. Measuring the unmeasurable. How did humans figure out how fast light travels? The story is a fascinating journey through scientific history. For thousands of years, people assumed light traveled instantaneously. After all, when you open your eyes, you see immediately, right? The ancient Greek philosopher Empedocles was one of the first to suggest that light had a finite speed, but he had no way to prove it. The first serious attempt to measure light speed came from Danish astronomer Ole Romer in 1676. He was studying Jupiter's moon Io, which disappears behind Jupiter regularly, like clockwork. But Romer noticed something odd. When Earth was moving away from Jupiter in its orbit, Io's eclipses appeared to happen later than predicted. When Earth was moving toward Jupiter, they happened earlier. Romer realized this was because light took time to cross the changing distance between Earth and Jupiter. Though his calculation wasn't perfectly accurate, he came remarkably close, about 220,000 kilometers per second. The scientific community finally accepted that light had a measurable, finite speed.
In 1849, French physicist Hippolyte Fizeau devised a brilliant experiment using a rapidly spinning toothed wheel. He would shine light through the gaps between the teeth, reflect it off a mirror several kilometers away, and measure whether the returning light was blocked by a tooth or passed through a gap. By adjusting the wheel's rotation speed, he could calculate how long the light took for its journey. His result? 315,000 kilometers per second, remarkably close to the true value. Later, American physicist Albert Michelson spent decades refining these measurements. Using rotating mirrors and precisely measured distances, he achieved incredible accuracy. By 1926, his measurements were within 99.9% of the modern accepted value. His work was so important that he became the first American to win the Nobel Prize in physics. Today, we define the meter itself in terms of light speed. 1 meter is the distance light travels in exactly 1/299,792,458th of a second. We've essentially flipped the script. We now know the speed of light with such precision that we use it to define distance rather than the other way around. Looking into the past. Here's one of the most profound implications of light's finite speed. When we look at distant objects, we're seeing them as they were in the past, not as they are now. The farther away something is, the further back in time we're looking. This makes astronomy a form of time travel. We can observe the universe's history simply by looking at increasingly distant objects. The Sun is about 150 million kilometers away, which means light from the Sun takes about 8 minutes and 20 seconds to reach Earth.
If the sun suddenly vanished, we wouldn't know it for more than 8 minutes. We'd keep feeling its warmth and seeing its light until that final batch of photons launched just before the sun's disappearance completed its journey to Earth. Then, darkness and cold would follow. The nearest star system to us, Alpha Centauri, is about 4.37 light-years away. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers or 5.88 trillion miles. When you see Alpha Centauri in the night sky, you're seeing light that left that star more than 4 years ago. If aliens living on a planet around Alpha Centauri were watching Earth through a powerful telescope right now, they would see our planet as it was 4 years ago. They'd be watching 2021 unfold, completely unaware of everything that's happened since. Many stars you see at night are tens, hundreds, or thousands of light years away. The beautiful Betelgeuse, that reddish star in Orion's shoulder, is about 550 light years away. The light reaching your eyes tonight left Betelgeuse around the year 1475, during the Renaissance, when Leonardo da Vinci was a young man. Betelgeuse might have already exploded in a spectacular supernova, but if it did, we won't know for centuries because the light from that explosion is still en route. When astronomers look at distant galaxies through powerful telescopes like the Hubble Space Telescope or the James Webb Space Telescope, they're seeing ancient history. Some galaxies are so far away that we see them as they were billions of years ago when the universe was young. The most distant objects we've observed are more than 13 billion light-years away. We're seeing them as they appeared just a few 100 million years after the Big Bang itself. Those galaxies might not even exist anymore. They may have changed beyond recognition or been destroyed in cosmic collisions. But their ancient light is just now arriving at our telescopes, delivering messages from the infant universe. Time dilation and the twin paradox. Einstein's special relativity reveals one of the strangest consequences of approaching light speed. Time doesn't flow at the same rate for everyone. It's relative, depending on how fast you're moving. This isn't just theoretical mathematics, it's been proven experimentally many times and must be accounted for in technologies we use every day. Imagine two twins, Alice and Bob. Alice boards a spacecraft that can travel at 90% of light speed and takes a journey to a star 10 light-years away and back. Bob stays on Earth. For Bob, the journey takes a bit over 22 years. He watches his twin spacecraft disappear into the cosmos, waits more than 2 decades, and finally welcomes her back, now 22 years older. But here's the shocking part. For Alice, the journey takes only about 10 years. When she returns, she's aged just 10 years, while her twin brother has aged 22 years. Alice is now 12 years younger than her identical twin. This isn't science fiction or a trick, it's what actually happens according to the laws of physics. Time genuinely passes more slowly for the person moving at high speed. The closer you get to light speed, the more dramatic this effect becomes. At 99% of light speed, time passes about 7 times slower for you than someone standing still. At 99.9% of light speed, it's about 22 times slower. At 99.99% of light speed, time is dilated by a factor of more than 70. This phenomenon is real and measurable even at much slower speeds. In 1971, physicists Joseph Haefel and Richard Keating conducted an experiment with atomic clocks. They synchronized several ultra-precise atomic clocks, kept some on the ground, and flew others around the world on commercial airliners. When the flying clocks returned, they were measured against the ground clocks. The flying clocks had lost a tiny fraction of a second, exactly as Einstein's equations predicted. The clocks had experienced time dilation. Today, this effect is crucial for GPS satellites. These satellites orbit Earth at about 14,000 kilometers per hour and are about 20,000 kilometers above the surface. Both their velocity and the difference in gravitational field strength mean that time passes differently on the satellites than on Earth's surface. If we didn't account for relativistic time dilation, GPS coordinates would drift by about 10 kilometers per day, rendering the system useless. Every navigation app on your phone relies on corrections for Einstein's relativity. Science fiction versions of light speed. Science fiction has long imagined ways to overcome the light speed barrier. Star Trek has warp drive, Star Wars has hyperspace, Battlestar Galactica has FTL jumps. These make for great storytelling, but they clash with our current understanding of physics. So are we forever trapped at sublight speeds? Maybe not, but the solutions are far stranger than simple go faster engines. The warp drive concept, while fictional in Star Trek, has a theoretical physics cousin called the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. The idea is clever. Instead of moving through space faster than light, you contract space in front of your ship and expand it behind you. The ship itself sits in a bubble of normal spacetime and never moves faster than light relative to its local environment. It's like standing on a moving walkway at an airport. You're not walking faster, but the floor is carrying you along. There's a catch, of course. Actually, several catches. The Alcubierre drive would require exotic matter with negative energy density, something we've never observed and might not exist. It would also need amounts of energy comparable to the mass energy of entire planets or stars. Even if we could build one, there's a serious problem. You couldn't steer it or turn it off from inside the warp bubble. You'd need to set your destination before engaging the drive, then hope you calculated correctly, because once you're inside the warp bubble, you're causally disconnected from its edges. Some scientists have explored whether wormholes, theoretical shortcuts through spacetime, might allow faster-than-light travel. Imagine spacetime as a sheet of paper. To go from one edge to another, light would travel across the surface. But if you could fold the paper and punch a hole through both layers, you'd create a shortcut. The wormhole itself wouldn't involve moving faster than light. You'd just be taking a shorter path through spacetime. But again, we'd need exotic matter to keep a wormhole open, and we have no idea if traversable wormholes can exist in nature. The hard truth is that with our current understanding of physics, interstellar travel faces severe limitations. Even if we could build a spacecraft that travels at 10% of light speed, which would be an extraordinary achievement, reaching even the nearest stars would take decades. Reaching interesting destinations like Earth-like exoplanets would take centuries or millennia. Generation ships, where multiple generations live and die during the journey, might be necessary. Or maybe we'll send artificial intelligence or robots as our ambassadors to the stars while humans stay home.
Why light speed matters for communication. The speed of light doesn't just limit travel, it fundamentally constrains communication across space. Any signal, whether radio waves, laser beams, or any other form of electromagnetic radiation, travels at light speed. This means interplanetary and interstellar communication faces unavoidable delays. When NASA's Mars rovers send data back to Earth, there's a time lag. Mars's distance from Earth varies as both planets orbit the Sun, ranging from about 55 million kilometers at closest approach to over 400 million kilometers at the far side of the Sun. At the closest distance, radio signals take about 3 minutes one way. At the furthest, it's about 22 minutes. This means when engineers on Earth send a command to a Mars rover, they have to wait 6 to 44 minutes for confirmation that the command was received and executed. This makes real-time remote control impossible. You can't drive a Mars rover with a joystick from Earth like a remote control car. By the time you see an obstacle and react, the rover would have crashed long ago. Instead, rovers must be semi-autonomous, able to make certain decisions themselves. Engineers send general instructions, drive to this location avoiding obstacles, and the rover figures out the details using its onboard computer. For the Voyager 1 spacecraft, currently the most distant human-made object, the situation is even more extreme. Voyager 1 is now over 24 billion kilometers from Earth, well into interstellar space.
Signals take more than 22 hours to reach it, and another 22 hours for any response to come back. A round-trip conversation with Voyager 1 takes about 45 hours. When engineers send a command, they wait nearly 2 days to learn if it worked. If we ever encounter intelligent life on planets around other stars, conversations would be incredibly frustrating. A message to a civilization orbiting Alpha Centauri would take 4.37 years to arrive, and their response would take another 4.37 years to reach us. A simple exchange of greetings would span nearly a decade. A conversation with a civilization 100 light-years away would see each question and answer separated by a century. You could ask a question as a child and receive the answer in old age, if you lived long enough. This fundamental limitation shapes how we might one day organize an interstellar civilization, if we ever become one. There could be no centralized government spanning multiple star systems because orders from a capital planet would arrive years or decades out of date. Each colony would need to be essentially autonomous, sharing news and culture with other human worlds, but making its own decisions. The light speed barrier doesn't just limit ships, it limits empires.
Faster than light particles? For decades, physicists were absolutely certain nothing could exceed light speed. Then, in 2011, an experiment called OPERA in Italy detected neutrinos that appeared to arrive 60 nanoseconds faster than light should allow. The scientific world went into a frenzy. Had we found an exception to Einstein's cosmic speed limit? Neutrinos are ghostly particles that barely interact with matter. Trillions pass through your body every second without you noticing. The OPERA experiment was measuring neutrinos created at CERN in Switzerland and detected at a laboratory in Italy 730 kilometers away. The apparent faster-than-light speed, if real, would have been one of the most important discoveries in physics history, potentially overturning special relativity. Scientists were appropriately skeptical. The OPERA team checked and rechecked their results. The physics community scrutinized every detail of the experiment. Other experiments tried to replicate the findings. Then, after months of investigation, the problem was found: a faulty fiber optic cable connection and a miscalibrated oscillator in the timing system. Once corrected, the neutrinos arrived exactly when they should, traveling at or just below light speed. Einstein's speed limit remained intact. However, there is a quirk worth mentioning. While nothing can travel through space faster than light, space itself can expand faster than light. In the early moments after the Big Bang, space underwent a period of inflation, expanding much faster than the speed of light. Even today, the most distant galaxies are receding from us faster than light because of the expansion of space between us and them. This doesn't violate relativity because the galaxies themselves aren't moving through space faster than light. The space between us is growing. It's a subtle but crucial distinction. There's also a phenomenon called quantum entanglement, where two particles can be connected in such a way that measuring one instantly affects the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to involve faster-than-light influence. However, it cannot be used to send information faster than light, so it doesn't violate causality or allow communication across interstellar distances instantaneously. The universe protects its speed limit cleverly. Light speed and the edge of the observable universe. The speed of light, combined with the age of the universe, determines how much of the cosmos we can ever observe. The universe is about 13.8 billion years old. You might think this means we can see 13.8 billion light years in every direction, for a total diameter of 27.6 billion light years. But the reality is far more interesting. Because space itself has been expanding during the time light has been traveling towards us, objects that emitted light 13.8 billion years ago have since moved much farther away.
The most distant objects we can see are now about 46 billion light-years away. This gives the observable universe a diameter of roughly 93 billion light-years. That's the cosmic horizon, the edge of everything we can possibly observe given the age of the universe and the speed of light. Beyond this horizon lies more universe, possibly infinite, that we can never see because light from those regions hasn't had time to reach us yet. No matter how powerful our telescopes become, there's a fundamental limit to how far we can observe. It's not a limit of technology, but a limit imposed by the speed of light and the age of the universe. Furthermore, because the universe is expanding at an accelerating rate, driven by mysterious dark energy, galaxies beyond a certain distance are moving away from us faster than light can travel. Light from those galaxies can never reach us. The observable universe is paradoxically shrinking in terms of how many galaxies we can theoretically reach or communicate with, even as it's expanding in physical size. Consider a galaxy currently 15 billion light-years away. Light leaving that galaxy today will never reach us because space is expanding faster than the light can traverse it. It's like a swimmer trying to cross a river that's widening faster than they can swim. Eventually, this galaxy will fade from view entirely, redshifted beyond detection. In the far future, trillions of years from now, intelligent beings in our galaxy, if any exist, will look out into space and see almost nothing. Nearly all galaxies will have been carried beyond the observable horizon.
Nearly all galaxies will have been carried beyond the observable horizon by cosmic expansion. Cherenkov radiation, when things seem to break the rules. While nothing can travel faster than light in a vacuum, particles can move faster than light travels through a medium like water or glass. Light slows down when passing through transparent materials. In water, for instance, light travels at about 75% of its vacuum speed, or roughly 225,000 kilometers per second. When charged particles, such as electrons, pass through water at speeds greater than 225,000 kilometers per second, but still less than 300,000 kilometers per second, the vacuum speed of light, they're moving faster than light moves through water. This creates a phenomenon called Cherenkov radiation, a brilliant blue glow. Imagine a particle as a boat on a lake. If the boat moves slowly, it creates gentle ripples that spread out ahead of it. But if the boat suddenly exceeds the speed that waves can travel on water, something different happens. The waves pile up behind the boat in a V-shaped wake. Cherenkov radiation is similar. The particle creates a shock wave of light analogous to the sonic boom created when aircraft exceed the speed of sound in air. This blue glow is what you see when looking at the water surrounding nuclear reactor cores. The reactor produces fast-moving particles, and when these particles zip through the water cooling system faster than light can travel in water, they emit this characteristic blue Cherenkov radiation. It's beautiful and eerie, an electric blue light that seems almost supernatural. Cherenkov radiation has practical applications. Scientists use it to detect high-energy particles in physics experiments. Massive underground tanks filled with ultra-pure water are surrounded by sensitive light detectors. When rare particles like neutrinos occasionally interact with the water, they can produce charged particles that emit Cherenkov light, which the detectors register. This allows scientists to study neutrinos and other exotic particles that would otherwise be nearly impossible to detect. The information speed limit. Beyond physical travel and light itself, there's a deeper principle at work. Information cannot travel faster than light. This is fundamental to causality, the idea that causes precede effects. If information could travel faster than light, it could, under certain circumstances, arrive before it was sent, creating paradoxes that would break the logical structure of the universe. Imagine you could send a message faster than light. According to relativity, different observers moving at different speeds would disagree about the order of events. For some observers, the message would arrive before it was sent. You could, in theory, send a message into your own past. This creates impossible scenarios. You could tell your past self not to send the message, but if you don't send it, you never receive it to tell yourself not to send it. The universe seems to forbid such paradoxes by enforcing a cosmic speed limit on information. Every experiment we've ever conducted confirms this. Quantum entanglement, despite connecting particles instantaneously across any distance, cannot transmit information faster than light. Radio waves, the fastest way we currently communicate, travel at light speed. Even if we discover exotic physics that allows some kind of faster-than-light phenomenon, it appears the universe has built-in safeguards preventing information from breaking causality. This has profound implications for the nature of reality. The speed of light isn't just a speed, it's the rate at which causality propagates through the universe. It's the speed of cause and effect itself. When you think about it this way, the speed of light becomes less about light specifically and more about the fundamental structure of space-time.
How light speed shaped the universe. In the early universe, immediately after the Big Bang, conditions were so hot and dense that light couldn't travel freely. Photons were constantly absorbed and re-emitted by the dense soup of particles. The universe was opaque, like trying to see through fog. This lasted for about 380,000 years after the Big Bang. Then, as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. This event, called recombination, made the universe transparent. Suddenly, light could travel freely through space. The photons released at that moment have been traveling ever since, stretched into microwaves by the expansion of space. We detect this ancient light today as the cosmic microwave background radiation, a faint glow of microwaves coming from all directions in the sky. This cosmic microwave background is the oldest light we can observe. It's a baby picture of the universe, showing us what conditions were like just 380,000 years after the beginning. We can't see further back because before recombination, the universe was opaque to light. The speed of light and the opacity of the early universe thus set a fundamental limit on how far back in time we can see using electromagnetic radiation. The speed of light also played a crucial role in the formation of the first stars and galaxies. After recombination, the universe entered a period called the Dark Ages, with no stars yet formed. Gradually, gravity pulled matter together into clumps. The first stars ignited, and their light began to spread through space at light speed, gradually illuminating the cosmos. The universe underwent reionization as starlight energized the hydrogen gas that filled space. This process took hundreds of millions of years, limited by how fast light could spread from the first stars. Measuring cosmic distances with light. Astronomers use light and its constant speed as a cosmic measuring stick. One of the most important techniques is to observe variable stars called Cepheids. These stars pulse with a regular rhythm, and there's a relationship between how bright they are actually and how fast they pulse. By measuring the pulse period, astronomers can calculate the star's true brightness. By comparing this to how bright it appears from Earth, they can determine its distance using the inverse square law. Light spreads out as it travels, getting dimmer with the square of the distance. For even greater distances, astronomers use Type 1a supernovae, exploding stars that all reach roughly the same peak brightness. By comparing their apparent brightness to this known standard, distances to galaxies billions of light-years away can be calculated. This technique led to one of the most shocking discoveries in modern cosmology. The universe's expansion is accelerating, driven by mysterious dark energy. There's also redshift, the stretching of light waves as space expands. When a galaxy is moving away from us due to cosmic expansion, its light is stretched to longer, redder wavelengths. The amount of redshift tells us how fast the galaxy is receding and, through Hubble's law, approximately how far away it is. The most distant galaxies we've observed have extreme redshift, their ultraviolet and visible light stretched all the way into the infrared part of the spectrum. All these techniques depend on light's constant speed. If light speed varied, none of these distance measurements would work, and our entire understanding of cosmic scales would collapse. The constancy of light speed is one of the most well-tested principles in physics, verified by countless experiments and observations over more than a century.
What if light speed were different? Here's a fun thought experiment. What if light traveled at a different speed? What if it were much faster or much slower? How would the universe change? If light were slower, say 30,000 kilometers per second instead of 300,000, the effects would be dramatic and strange. You'd notice a delay when switching on a light in a large room. Watching a baseball game from the outfield seats, you'd see the batter hit the ball noticeably before you heard the crack of the bat. Lightning and thunder, instead of being separated by seconds, might arrive nearly together. GPS satellites would need completely different relativity corrections. And looking at the night sky, you'd be seeing much more recent history. The sun would appear as it was just 50 seconds ago instead of 8 minutes ago. Atomic and molecular structures would be different too. The speed of light is intimately connected to the electromagnetic force, which holds atoms together. If light speed were significantly different, atoms might be larger or smaller. Chemical bonds might be stronger or weaker, and the periodic table of elements might look entirely different. Life as we know it probably couldn't exist. If light were infinitely fast, arriving everywhere instantaneously, special relativity would fail. There would be no time dilation, no length contraction, no mass-energy equivalence. The famous equation E = mc squared wouldn't make sense. Cause and effect would be absolute, with everyone agreeing on the order of events regardless of their motion. The universe would operate more like our intuition suggests, but it would be fundamentally different from the reality we inhabit. Interestingly, the speed of light isn't just some arbitrary number the universe picked at random. It's related to other fundamental constants of nature, the permittivity and permeability of free space, which describe how electric and magnetic fields behave in vacuum. The speed of light falls out of Maxwell's equations for electromagnetism as a consequence of these properties. Change light speed and you change the nature of electromagnetism itself, cascading through all of physics. The speed of darkness. Here's a quirky question that often comes up. Can darkness travel faster than light? The answer depends on what you mean by darkness. If you think of darkness as simply the absence of light, then it doesn't travel at all. Darkness isn't a thing, it's the lack of a thing. When you turn off a light, darkness doesn't rush in. Light simply stops being emitted, and the room goes dark at the speed at which the last photons leave. But here's where it gets interesting. If you create a shadow, that shadow can appear to move faster than light under certain circumstances, without violating relativity. Imagine you're holding a laser pointer, standing on Earth and pointing at the moon. If you quickly sweep the laser beam across the moon's surface, the spot of light moves very fast. Now imagine you're illuminating a surface much farther away, say a distant wall in space. If you rotate the laser quickly, the spot on that distant wall could sweep across it faster than light speed. The shadow's edge moving across the wall can exceed light speed because it's not a physical object, it's an information about where light is and isn't. No matter, energy, or information is actually traveling along the shadow's edge. Each point on the wall is independently illuminated or not by photons that travel at light speed.
The pattern of illumination can change faster than light, but no individual photon or signal exceeds c. This is similar to how scissors work. When you close scissors, the point where the blades meet can move along the blade faster than you're moving your hand, depending on the angle of the blades. With a very shallow angle and fast hand motion, that crossing point could theoretically exceed light speed. But again, no physical object is moving that fast, just a geometric pattern. Light speed and time travel. One of the most tantalizing implications of Einstein's relativity is that light speed opens a door to time travel, but only in one direction, forward. We've already discussed time dilation, where moving fast makes time pass slower for you relative to stationary observers. But let's dive deeper into what this means for actual time travel. Imagine a spacecraft that could accelerate to 99.9999% of the speed of light. At this speed, time dilation becomes extreme. For every year you experience inside the spacecraft, about 707 years pass on Earth. If you took a round trip lasting 10 years by your onboard clock, you'd return to Earth 7,070 years in the future. You would have effectively traveled through time, skipping over millennia in what felt like a decade to you. This isn't theoretical speculation, it's a consequence of proven physics. Time dilation has been measured at much lower speeds. Astronauts on the International Space Station, orbiting at about 28,000 kilometers per hour, age slightly slower than people on Earth. After 6 months in orbit, an astronaut has aged about 0.007 seconds less than their Earthbound counterparts. It's tiny, but measurable and consistent with relativity. The closer you get to light speed, the more dramatic the effect becomes. At 99.99999% of light speed, 1 year for you equals about 2,236 years on Earth. You could witness humanity's far future firsthand. But there's a catch. You can never return to your own time. There's no going backward. The past is sealed off from us by the laws of physics. You could travel to the year 10,000 CE, but you could never return to 2025. Some physicists have explored exotic scenarios involving wormholes or rotating black holes that might theoretically allow backward time travel. These solutions exist mathematically in Einstein's equations, but they require conditions so extreme, like infinite rotating cylinders or traversable wormholes stabilized by exotic matter, that most scientists doubt they're physically possible. The universe seems to protect causality, preventing paradoxes where you could meet your past self or prevent your own birth. What about cosmic strings, hypothetical defects in space-time left over from the Big Bang? Some theories suggest that if two cosmic strings passed by each other at nearly light speed, they might warp space-time enough to create closed time-like curves, paths through space-time that loop back to their starting point in time. But cosmic strings remain hypothetical, and even if they exist, exploiting them for time travel seems impossibly difficult. The most realistic form of time travel available to us is cryogenic freezing or suspended animation, though this is still science fiction. If we could safely freeze a person and revive them centuries later, they would wake up in the future. Combined with time dilation during relativistic space travel, humans might one day explore the far future, becoming cosmic time travelers, though always moving forward, never back. Gravitational waves, ripples at light speed. In 2015, humanity achieved something remarkable. We detected gravitational waves for the first time. These are ripples in the fabric of space-time itself, and they travel at exactly light speed. This discovery opened an entirely new way of observing the universe and confirmed yet another prediction of Einstein's general relativity. Gravitational waves are created by massive objects accelerating violently, such as two black holes orbiting each other and spiraling inward until they merge. As they orbit, they create waves in space-time that spread outward at light speed, like ripples on a pond when you throw a stone. These waves are incredibly weak by the time they reach Earth. The first detected gravitational wave came from two black holes merging more than 1 billion light-years away, and by the time the wave reached us, it stretched and squeezed space by less than 1,000th the width of a proton.
To detect something so minuscule, scientists built LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO uses two facilities in Louisiana and Washington state, each with two 4-kilometer-long arms arranged in an L shape. Laser beams bounce back and forth along these arms thousands of times, and when a gravitational wave passes through, it stretches space in one direction and compresses it in the other. The incredibly sensitive detectors can measure these tiny changes. What's remarkable is that gravitational waves travel at light speed, not faster or slower. This tells us something profound about the nature of gravity. In Newton's view, gravity was instantaneous. If the sun suddenly vanished, Earth would immediately fly off into space. But Einstein showed that gravity, like light, has a speed limit. If the sun vanished, Earth would continue orbiting for about 8 minutes and 20 seconds, the time it takes for the information that the sun is gone to reach us at light speed. Gravitational waves also give us a new tool for astronomy. Unlike light, which can be absorbed or scattered by dust and gas, gravitational waves pass through everything almost unimpeded. We can use them to observe events that would be invisible to traditional telescopes, like black hole mergers or the cores of supernovae. In 2017, LIGO detected gravitational waves from two neutron stars merging, and within seconds, telescopes around the world turned to observe the same event in light. This multi-messenger astronomy, combining gravitational waves and electromagnetic radiation, gives us a richer understanding of cosmic events. The fact that gravitational waves travel at light speed reinforces that C isn't just about light, it's a fundamental property of space-time itself. It's the maximum speed at which any massless wave or particle can travel, whether photons, gravitons, the hypothetical particles of gravity, or any other force carrier. Light speed in different materials. We've mentioned that light slows down when passing through transparent materials, but let's explore this phenomenon more deeply. In vacuum, light travels at its maximum speed of 299,792 kilometers per second, but in glass it's slower to about 200,000 kilometers per second. In diamond, it's even slower, about 124,000 kilometers per second. In water, as we discussed, it's about 225,000 kilometers per second. This slowing happens because light interacts with the atoms in the material. When a photon enters glass, it's absorbed by an atom which becomes excited. Almost immediately, the atom releases a new photon. This process repeats countless times as light passes through the material. Each absorption and re-emission takes a tiny amount of time, and the cumulative effect is that light appears to travel more slowly through the material. The ratio of light speed in vacuum to its speed in a material is called the refractive index. Vacuum has a refractive index of 1 by definition. Water's refractive index is about 1.33. Glass is typically around 1.5, and diamond is about 2.42. The higher the refractive index, the more light bends when entering the material, and the slower it travels within. This bending, called refraction, is why a straw in a glass of water appears bent or broken at the water's surface. Light from the submerged part of the straw bends as it exits the water and enters air, changing direction and creating the optical illusion. It's also why swimming pools appear shallower than they actually are, and why lenses can focus light to create images. There's an exotic state of matter called a Bose-Einstein condensate, where physicists have slowed light to just 17 meters per second, about 38 miles per hour, slower than a car on a residential street. They achieved this by passing light through a Bose-Einstein condensate of sodium atoms cooled to within a few billionths of a degree above absolute zero. Even more remarkably, in 2001, Howe's team completely stopped light, storing it in the condensate, and then released it again. The light pulse entered the condensate, was converted into an atomic excitation pattern that essentially remembered the light, and then was converted back into light and released. This has potential applications in quantum computing and information storage, where you might want to capture, store, and retrieve quantum information carried by photons. At the opposite extreme, there are materials with a negative refractive index, so-called metamaterials engineered at the nanoscale. These materials can bend light in unusual ways, potentially enabling superlenses that exceed the normal resolution limits of optical microscopes, or even theoretical invisibility cloaks that route light around an object. While true invisibility cloaks remain mostly theoretical, researchers have demonstrated proof-of-concept devices that can hide small objects from certain wavelengths of light.
The Doppler effect and light. You've probably experienced the Doppler effect with sound. When an ambulance approaches with its siren blaring, the pitch sounds higher, and as it passes and moves away, the pitch drops lower. This happens because the sound waves are compressed as the ambulance approaches, shorter wavelength, higher frequency, and stretched as it recedes, longer wavelength, lower frequency. Light exhibits the same effect, and it's crucial for astronomy. When a star or galaxy moves toward us, its light is compressed to shorter wavelengths, shifting toward the blue end of the spectrum. This is called blue shift. When it moves away, the light is stretched to longer wavelengths, shifting toward the red end. This is redshift. Astronomers use redshift to measure how fast distant galaxies are moving away from us. In the 1920s, Edwin Hubble discovered that nearly all galaxies show redshift, and that the farther away a galaxy is, the faster it's receding. This was the first evidence that the universe is expanding. The relationship between distance and recession velocity is called Hubble's law, and it's one of the foundations of Big Bang cosmology. The most distant galaxies have enormous redshifts. Light that was originally ultraviolet when it left those galaxies billions of years ago has been stretched all the way into the infrared part of the spectrum by the time it reaches us. The James Webb Space Telescope was specifically designed to observe in the infrared to study these ancient, highly redshifted galaxies. There's also relativistic Doppler shift, which accounts for time dilation when objects move at a significant fraction of light speed. At everyday speeds, the classical Doppler formula works fine, but when objects approach relativistic speeds, you must use the relativistic formula that includes time dilation effects. This becomes important when studying quasars, jets from black holes, and other extreme cosmic phenomena where matter is accelerated to near-light speeds. Police radar guns use the Doppler effect with radio waves to measure car speeds. The radar gun emits radio waves that bounce off a moving car. If the car is approaching, the reflected waves have a higher frequency, if receding, lower. The frequency shift reveals the car's speed. It's the same principle astronomers use to detect exoplanets, planets orbiting other stars. As a planet orbits, it causes its star to wobble slightly. This wobble creates tiny Doppler shifts in the star's light, alternating between redshift and blue shift as the star moves toward and away from us. By measuring these shifts, astronomers can detect planets and estimate their masses and orbital periods. Photography and the speed of light. Every photograph is a time capsule, capturing light that left objects at different times depending on their distances. When you take a photo of a landscape, the light from the nearby tree left microseconds before the light from the distant mountain. For terrestrial photography, these differences are negligible, but when photographing the night sky, you're capturing light from different eras. Consider a photograph of the night sky that includes the moon, Jupiter, and a distant star. The moonlight you captured left the moon about 1.3 seconds before you pressed the shutter. Jupiter's light left between 33 and 52 minutes earlier, depending on where both planets were in their orbits, and the starlight might have left decades or centuries ago. Your single photograph captures multiple moments in time, assembled into one image by your camera. Astrophotographers taking pictures of galaxies are photographing ancient light. A photo of the Andromeda Galaxy, our nearest major galactic neighbor, shows Andromeda as it appeared 2.5 million years ago. Early humans were just beginning to use stone tools when that light began its journey. By the time it reached your camera sensor, all recorded human history had elapsed. High-speed photography can freeze moments briefer than we can perceive. Modern cameras can capture images with exposure times of 1,000th or even 1/10,000th of a second. But even these are slow compared to the speed of light. In 1 microsecond, light travels 300 meters. In the time it takes a camera to snap a photo at 1/8,000th of a second, light has traveled 37.5 kilometers. There's a technique called light-in-flight photography, where researchers use incredibly fast cameras to actually watch light itself move through a scene. In 2011, researchers at MIT developed a camera system that could capture 1 trillion frames per second. At this speed, they could record a pulse of light as it traveled through a bottle, seeing the light move from one side to the other. It's like slow-motion photography, but for light itself. To the camera, light appears to crawl across the scene, revealing its motion frame by frame. This technology has applications beyond scientific curiosity. It could be used to see around corners by capturing light that bounces off walls and other surfaces, analyzing the patterns to reconstruct hidden objects. It might improve medical imaging, letting doctors see inside the human body with unprecedented detail. And it helps researchers study ultra-fast phenomena like laser interactions, chemical reactions, and the behavior of materials on timescales where even light seems to move slowly.
Light speed and quantum mechanics. Quantum mechanics, the physics of the very small, has a complex relationship with light speed. Photons, the particles of light, are quantum objects that behave both as particles and waves. This wave-particle duality is one of the strangest features of quantum mechanics, and light speed plays a central role. According to quantum field theory, the modern framework combining quantum mechanics and special relativity, particles don't really travel in the classical sense. Instead, they're excitations in quantum fields that permeate all of space. A photon is an excitation in the electromagnetic field, and it propagates through this field at light speed. It doesn't accelerate from rest to light speed. It's created already moving at c and must always move at exactly this speed. There's an important principle in quantum mechanics called the Heisenberg uncertainty principle. It states that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of measurement technology, it's a fundamental feature of nature. Particles don't have definite positions and momenta until you measure them. For photons traveling at light speed, there's an interesting consequence. From the photon's perspective, if such a perspective made sense, no time passes. A photon emitted from a distant galaxy billions of light years away experiences no passage of time during its journey. From its reference frame, it's emitted and absorbed instantaneously. Of course, this is a thought experiment. We can't actually adopt a photon's reference frame because the equations of relativity become undefined at exactly light speed. But it illustrates the strange nature of light speed travel. Quantum mechanics also predicts vacuum fluctuations, brief moments where particle-antiparticle pairs spontaneously appear and disappear in empty space. These virtual particles pop in and out of existence so quickly they don't violate conservation of energy, thanks to the uncertainty principle. These fluctuations happen everywhere, constantly, even in the vacuum of space. And interestingly, they respect the light speed limit. Information cannot be transferred faster than light, even using quantum vacuum fluctuations. There's also the quantum Zeno effect, where frequent observations can freeze a quantum system, preventing it from changing state.
If you measure a quantum system frequently enough, it remains in its initial state, unable to evolve. It's as if watched pots really never boil in the quantum world. This effect is related to how measurement collapses quantum states, and importantly, it doesn't violate causality or allow faster-than-light signaling. The universe is very good at protecting its speed limit, even at the quantum level. Black holes and light speed. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape from within the event horizon. The event horizon is the boundary of no return. Cross it and you're trapped forever, doomed to fall into the singularity at the center. This makes black holes the ultimate prisons, places where the cosmic speed limit becomes a sentence. But let's think about what happens as you approach a black hole. As you get closer, the gravitational pull strengthens. According to general relativity, gravity warps space-time, and intense gravity slows down time. If you watched a clock falling toward a black hole, you'd see it tick slower and slower as it approached the event horizon. The clock would never quite seem to reach the horizon. Its image would freeze, redshifted to invisibility, as the light carrying information about it became infinitely stretched. From the falling clock's perspective, however, time passes normally. It crosses the event horizon without any local indication that something special has happened, and continues falling toward the singularity. This difference in perspectives is one of the paradoxes of black holes, and has led to deep questions about what happens to information that falls into a black hole, the black hole information paradox. Near a black hole, space is so warped that light itself can orbit. There's a region called the photon sphere, located 1.5 times the Schwarzschild radius, the event horizon radius, from the black hole's center. At this distance, light can travel in circular orbits around the black hole. If you were at the photon sphere and looked forward, you might see the back of your own head as light from you circled the black hole and returned. Inside the event horizon, something even stranger happens. The roles of space and time swap in a sense. Just as you can't stop moving forward in time outside a black hole, inside the horizon, you can't stop moving inward toward the singularity. It becomes as inevitable as the future. The singularity isn't a place in space, but a moment in your future, a moment when space-time curvature becomes infinite and our physics breaks down. Black holes also produce intense radiation called Hawking radiation, predicted by Stephen Hawking in 1974. Due to quantum effects near the event horizon, black holes slowly evaporate, emitting particles and energy. The radiation is caused by virtual particle pairs at the horizon, where one particle falls in while the other escapes. From far away, it looks like the black hole is radiating. This process is incredibly slow for large black holes, but means that even black holes aren't eternal. Given enough time, trillions upon trillions of years, even the most massive black holes will evaporate completely. Hawking radiation doesn't exceed light speed, but it does mean that black holes aren't completely black. They glow with thermal radiation, though for stellar mass black holes, this glow is far colder than the cosmic microwave background and effectively undetectable. Only tiny black holes would radiate significantly, and these would evaporate quickly in a final explosion of energy.
Light speed in popular culture. Science fiction has long been fascinated with light speed and the challenge it presents for interstellar civilizations. Let's look at how various fictional universes have addressed the light speed barrier and what they get right or wrong from a physics perspective. Star Trek's warp drive explicitly doesn't violate relativity because the ship isn't moving through space faster than light. Space itself is contracting ahead and expanding behind, carrying the ship along. This is conceptually similar to the Alcubierre drive. However, Star Trek largely ignores the time dilation that would affect the crew during sublight travel.
When the Enterprise travels at impulse power, significant fractions of light speed, the crew should age differently than people on planets, but this is rarely addressed. Star Wars' hyperspace is different. Ships enter an alternate dimension where faster-than-light travel is possible. This sidesteps relativity entirely by essentially saying, different universe, different rules. From a physics perspective, there's no evidence such an alternate dimension exists, but it's internally consistent within the Star Wars universe. The movie Interstellar, advised by physicist Kip Thorne, takes a more scientifically grounded approach. Time dilation is a major plot point. When the crew visits a planet near a massive black hole called Gargantua, they experience extreme time dilation. 1 hour on the planet equals 7 years outside. This accurately represents what general relativity predicts, though the specific numbers are dramatic even for proximity to a black hole. In the Planet of the Apes franchise, the original, astronauts traveling at near light speed experience time dilation. They travel for months by their clocks, but return to find Earth thousands of years in the future. This is physically accurate. Time dilation at near light speeds really would allow you to reach Earth's future. The Ender's Game series by Orson Scott Card realistically depicts the challenges of interstellar war when communication and travel are limited by light speed. Characters make journeys lasting years or decades, aging much slower than those on their home worlds due to time dilation. By the time they return from missions, everyone they knew has aged or died. It's emotionally wrenching and scientifically accurate. Some science fiction explores generation ships, vessels that take centuries or millennia to reach other stars, with multiple generations living and dying during the journey. This is perhaps the most realistic approach to interstellar colonization with current or near-future physics. No exotic materials, no new physics, just patient engineering and social systems that can maintain themselves across centuries. Interestingly, many video games ignore light speed limits for gameplay reasons. In most space games, you can communicate instantly across star systems, which would be impossible in reality. Imagine a multiplayer game where messages took years to arrive. It would be more realistic, but far less fun. Game designers prioritize enjoyable experiences over physical accuracy, which is reasonable for entertainment. The future of light speed research. What frontiers remain in our understanding of light speed? What experiments and observations might deepen our knowledge or even reveal surprises? One active area is testing whether light speed is truly constant across the entire history of the universe. Some theories suggest that physical constants might have changed over billions of years. By examining light from extremely distant ancient quasars, astronomers can look for evidence that light speed, or the fine structure constant, which depends on light speed, was different in the early universe. So far, measurements suggest these constants have remained remarkably stable, but the search continues with ever greater precision. Researchers are also exploring whether light speed might vary slightly depending on the photon's energy in some theories of quantum gravity. These theories suggest that at the extremely tiny Planck scale, space-time might be discrete or foamy rather than smooth. High-energy photons might travel infinitesimally slower than low-energy photons. Gamma-ray bursts, the most energetic explosions in the universe, emit photons across a huge energy range that have been traveling for billions of years. By comparing the arrival times of high and low-energy photons, scientists can test whether they traveled at exactly the same speed. So far, results show no difference, placing tight constraints on quantum gravity theories. There's also research into faster-than-light communication via quantum entanglement. While mainstream physics says this is impossible, researchers continue to explore the boundaries of what entanglement can and cannot do. So far, all experiments confirm that entanglement cannot transmit information faster than light, preserving causality. But the research has deepened our understanding of quantum mechanics and led to practical applications like quantum cryptography and quantum teleportation of quantum states, not physical objects. Some physicists study hypothetical particles called tachyons that would travel faster than light. If they exist, tachyons would have imaginary mass and strange properties like moving faster when they lose energy. No tachyons have ever been detected, and most physicists believe they're mathematical curiosities rather than real particles. But searching for them helps us test the limits of our theories. There's ongoing work on the Alcubierre warp drive concept. While the original proposal required negative energy equivalent to Jupiter's mass, refined versions have dramatically reduced this requirement. Some calculations suggest it might be possible with the negative energy equivalent to just a few hundred kilograms, though this still requires exotic matter we don't know how to create. Research continues into whether warp drives could ever be practical, or if they remain confined to the realm of theory. Looking further ahead, some scientists speculate about manipulating the vacuum of space itself. If we could change the properties of vacuum, we might change the local speed of light. This is extraordinarily speculative, venturing far beyond proven physics, but it illustrates how researchers think about future possibilities. If space-time has properties we can manipulate, maybe the cosmic speed limit sign could be adjusted, at least locally.
Light speed and our place in the cosmos. The speed of light is far more than just a velocity. It's a fundamental constant that shapes the universe's structure, determines how we perceive reality, sets ultimate limits on travel and communication, and connects space with time in ways that defy everyday intuition. Understanding light speed means accepting that the universe is stranger and more wonderful than it appears. Time is relative. The past, present, and future depend on your motion. The stars you see aren't where they are now, but where they were years or centuries ago. Nothing can travel from here to there faster than light can make the journey, making the cosmos vast beyond comprehension and forever placing most of it beyond our reach. Yet this cosmic speed limit also makes the universe knowable. Because light speed is constant for everyone, regardless of their motion, we can trust our observations. We can measure distances, determine ages, understand how stars and galaxies work. The photons arriving at our telescopes have traveled reliably through space, carrying accurate information about their sources. Light speed reminds us of both our capabilities and our limitations. We've sent spacecraft beyond our solar system, communicated across space, taken pictures of distant galaxies, and verified Einstein's predictions to extraordinary precision. Yet we're also reminded that the universe is vast, that our cosmic neighborhood is limited by the speed at which light and information can travel, and that the stars, for all their beauty in our night sky, remain almost impossibly distant. Perhaps most profoundly, the speed of light tells us something deep about the nature of reality itself. It's not just a speed limit for motion, but a fundamental feature of space-time. It's the rate at which cause and effect propagate, the speed at which the universe communicates with itself. In a very real sense, the speed of light is the speed of reality unfolding. Every time you look at a star, you're seeing across both space and time. You're looking at history, at light that began its journey before you were born, perhaps before humanity existed, carrying news from distant suns. The photons entering your eye at this moment have traveled unimaginable distances at this cosmic speed limit, just to end their journey by giving you a glimpse of the universe. And that's beautiful. Light speed isn't just a number, it's a reminder that we live in a universe governed by elegant laws, where even something as simple as the speed at which light travels connects everything from the smallest atomic particles to the largest structures in the cosmos, from the flow of time to the fate of the universe itself. Understanding light speed is understanding our place in the cosmos, travelers on a small planet looking outward at a universe that reveals its secrets one photon at a time, each arriving at exactly 299,792,488 meters per second, neither faster nor slower, bound by laws we're only beginning to fully comprehend. The speed of light is the universe's way of saying, slow down, pay attention, and appreciate the journey.